various attendants from different countries and different time zones. So I hope everybody can join with their own, schedule without any problem. Okay, thank you. In today's webinar, we will discuss about the data center HVAC system design. Previously, we already discussed some uh, HVAC design for general applications such as residential and for comfort. But today we will discuss something that is become very hype in engineering application. Uh, Not only for HVAC engineers, but also the world using AI or maybe technology boom like cloud computing. But HVAC become one crucial part in this system. Before I get started in this topic, let me introduce myself again. So my name is Viratama. I've been around in CFD and consulting industry since 2013 with the company PT Tensor. And currently we developing some softwares. First is the Tensor HVAC Pro, which is the part of Tensor CFD program, which is dedicated HVAC CFD simulation for easy to use and doesn't have any expertise in CFD. And we also currently develop Tensor Beam 3D, which is text to beam design software. So you can just simply type your design requirement, like design me a house with 5 to 8 meters, let's say with 2 or 3 rooms. And it will be launched around March. So stay tuned with this. Yeah, this software is standalone software, but can also be used to to design a system for Tensor FEAC Pro. So they are complementing each other. And my last education is from New York University, mechanical engineering, master degree. So I will be mainly talking in my perspective as mechanical engineer. But the software itself, Tensor SAC, is actually designed for not only mechanical engineers like civil and also architect. So yeah, you don't have to be mechanical engineers to use this software. Okay, let's start our discussion about data center energy. Data center. Like I said previously, our world is dominated by digital technology that using websites daily. We cannot live without websites today for our daily use for shopping, let's say, or maybe gathering information even for works. And cloud computing also become one standard in industry. You don't have to worry about your hardware, let's say, or maybe uh, you can save large amount of data without collaborative easily in the different side of the world. And cryptocurrency, crypto mining, and anything else, all of those cannot possibly be used without data center. So data center is basically computers or server that starts your data on the cloud. Cloud is basically just data centers, but it has some concentration of hardwares there. So it will consumes a lot of energy, dissipates high amount of heats, and because you expect your data to be accessible every day, every time you need, even 1 minute in maintenance or 1 hour in maintenance will makes your project, like waste of time and waste of money. So the data center should be designed to be very reliable with so many redundant system, and it will never shut down 24 hours a day, 165 day a year. So it literally cannot shut down. And if the data center is shut down, it has some problem, let's say, of course, it will be a huge problem for the business. And this is also true, of course, for the HVAC design. If we design the HVAC for data center is not reliable enough, the overall performance, of course, will also be affected. And this is some data that will give you some, big picture about how the countries that use energy for data centers. This is in terawatt hour, which is huge. Mostly now is in the United States and also in China. But the thing that I want to emphasize is that the huge amount of energy used here in terawatts hour. So it consumes a lot of energies from your, uh, power generator, or maybe your energy from oil, let's say, or from coal. If some countries still use coal, will be used for data center operation, which is at the end will also have impact to the environment and sustainability. And here, why HVAC in data center is so important. So around 50% of the energy used in the data center is used by its cooling system. So basically, if you design a better cooling system, better HVAC system for your data center, you basically create it more sustainable for the planet. You save the planet. You can say that. It's a huge amounts of energy, and again, in this design process, we will face a lot of trade-offs between the technology of reducing costs and maximizing cooling performance. That's what we will discuss in this meeting. Okay, let's discuss the data center facility. So here we have, like a general setup for data center facility. So basically, we have some office there with some staff there, and also some HVAC system for the office. And we also have the server room here, which has different HVAC system. And this is again the general overview of the HVAC system in data center. So basically, we have some servers in specific rows, and we have one or more, the CARIC or CAIH, which we will discuss later, which is basically the unit that handles the air, that cools the air, or maybe moving the air around that system. So we have one or more of these to be able to circulate the air, or maybe the fluid if we use the fluid cooling system. And this is basically how it works. It just the unit, the CRAC unit, just pulling the hot air and make it cool basically, and just distribute back to the system. But it's not that easy. We will discuss that later. Okay, why data centers have high heat dissipation? We know from our laptops or our computer, we can see that if we use a lot of CPU power or maybe RAM, you will notice that the fans move faster with higher RPMs. That's because of the heat dissipation from your CPU or your CPU. Then why it has to be cooled? Of course, if you have overheat CPU, it will blow up your system. It will be literally burned or smokes, and will be destroy your system permanently. Or at some point, let's say around, I don't know, below 100 degrees, if you don't maintain it below that certain amount of level, that will be also reducing your performance of computation, because we use semiconductor to move electrons. We know that the temperature will affect the electron moving performance. And the data center is not only consist of CPU, of course. We have some other system like routers, switches, hubs, and also some maybe audio visual like the buttons and anything else that also dissipates energy, that we have also to manage the heat in some level, in some acceptable level. And all of those systems are stored in a shelf rack. So in a rack with maybe has height around 2 meters, will be stacked in a specified number of rows. And why the data center HVAC is different from residential or maybe office HVAC system? The major thing that makes this difference is the energy density. So human, like we discussed in previous discussion about human metabolism, will only generate around 400 or 50, 55, 450 BTU per hour, which is much less compared to the data center. For air cooled, it dissipates around 17,000, and the air cooled, and the liquid cooled is around 100,000 BTU per hour, which is much higher than 100%, 100 times more. That's why in data center we don't expect the comfortable airflow or maybe noise that we will comfortably live in that server, but sometimes we have to use air plug or to reduce the noise level. It will be very noisy there because high velocity of air move around that system. And here the air cooled is maybe much less energy density compared to liquid cooled, because we know that air cooled first has 10 times density compared to air cooled, and the heat capacity of liquid is much more larger than the air cooled, so it basically better dissipates energy. But we know that liquid cooled is not as easy to install, let's say, for electronics appliances. So we have to purchase some special tools or maybe some special vendors. But in reality, we use both in our system. Sometimes we have different or various energy density in different racks. So yeah. Okay, first method that used in data center cooling is air cooling. So in the air cooling, as its name suggests, is just basically blows air in in the parallel dimension with the racks. So racks basically has some stacked of systems that allows the air to blow around its level of these racks. So its level has its own heat dissipation that has to be cooled with the air. Just like your PC or maybe your laptops that have fans, but it cools with the air from the outside, or maybe local fans that we will use. We will see later. Okay, the other method is water cooling. Again, as its name suggests, we just simply pump or chilled water to the system and supply it to the to the system. So basically, if you have hot CPU or hot routers, we just make some local system that flows the liquid around that system. Of course, it is also have some various technologies that used in today's in the industry with different type of liquids, but mostly used water because it is widely available in our environment. Okay, and this is maybe one different construction strategy that used in the HVAC system of a data center. So in data center, we use a raised floor system. So we have certain amount of height in the floor. So the air will be supplied through this, underneath our racks, and this high pressure under this floor will supply the cold air to the server room, and then the flow will pass through these racks. So yeah, most of the data center building will have this raised floor for this purpose, but not all. Sometimes we also have some local system above the floor that we will discuss later. But this is again the most commonly used strategy for the data center HVAC air distribution. Okay, this is the CRAC, or computer room air conditioner, or CRAH, computer room air handler. It's basically just like an air handling unit in your HVAC system. It consists of the fans. This is the main part of this system. So the fans will move the air basically, and we also have to have the cooling coil with chilled water here. So it sucks the high temperature air and cool it down, and then distribute it again in the system. And we can also have humidifier or dehumidifier, and also filter to better manage the system or the air. So what is the difference between CRAH and CRAC? This is like some general differences between them. So for CRAC, we have direct expansion cooling. We use refrigerant, and it has compressor in it, and also have higher power usage. But for CRAH, we only use the chilled water. We don't use refrigerant or compressor, and it has lower power usage. Of course, again, it will be depend on your detailed system specification when to use one of these selection. But basically, they are just the same, just distributing the air and cool it down. Just different detailed system. We will not discuss this in this detail today. Okay, let's discuss about the cooling strategy. So from our previous discussion, we know that we have cooled air that has to be flows to the racks in order to cool it down. We have some options to maximize the cooling strategy. First is to design the room. So basically, you design the layout to make the airflow, don't circulate back or something similar to maximize the efficiency. Or we can change the aisle. So let's say we can close the aisle air flow, let's say, to make your system more efficient. Or we can just modify the racks, maybe change some racks with some local fans to move the air uh, distribution around this. Okay, let's first discuss why we have to manage the air properly. We have to prevent the hot and cold air from missing before it enters or before it touch the racks. Let's say if we have cold air directly from our air handling unit and it touch directly to the hot air, of course we will get hot air that try to cool the server. The result will be so not effective because let's say we will get some higher value of temperature for the racks, which is not good for the performance. On the other hand, if we have too much or too cold air that not distributed well, we will lose a high amount of energy to cool the air, but don't have a better result. Just basically just like designing the air conditioning system. And if we don't design the airflow properly, it will also cause some problem like the circulating problem. So if you have hot air here and it move recirculating back to this aisle and mixed with the cold air, it will be again makes the air hot before even touch the racks, which is not good for the performance. And that's why here we have to have a good understanding in air management, whether with some existing context, existing best practices, or with analytics tool like computational fluid dynamics, which we will discuss in the end of this discussion. Okay, the one thing that we can do in order to manage the airflow is use the containment. So basically we add some walls to make the flow directed the way we want. Let's say we put some some airflow duct system here, or maybe close right here to maximize the mass flow rate without to prevent the recirculating problem. It will increase the efficiency of the cooling and also have a uniform inlet temperature because we eliminate the recirculating problem. But it will increase your budget. It will add your cost of materials and also works. And yeah, again, that is engineering. We have to deal with some trade-off between the cost and efficiency of performance. This is the first example of containment. So it is the cold aisle. So we basically close or contain the cold aisle here to make sure that the flow of the cold air is not moving upward and recirculate here. Or it prevents the hot air to recirculate from the top of this aisle. So you can see from this example, we have containment here with the glass. So it's actually basically the containment. We can notice that this is the cold aisle because we know that the tiles here are perforated for the cold air to move from the bottom of the uh, floor. And yeah, this is the cold aisle containment. And this is maybe the detailed diagram to explain how it works. It's just basically from your system, CRAC or CRAH, with the fans blows down here, and yeah, we contain some cold aisle to prevent it from recirculates back. And on the other hand, we can also use hot aisle containment. So basically the same thing. We contain the hot aisle to make this system not recirculating back to the cold aisle. And yeah, one of every option of this has its own advantages and disadvantages, but it all depends on the detailed system or the requirement of the users. Okay, it's the same thing for the the detail of it. And the last strategy that we can also use is use the in-row cooling. So in each rows, we modify one of the rack to use the local fans here. So we don't have to make the raised floor to make the cooling, possible. So it will save the fan energy from CARC or CRAH. And one of the important advantage here is you can handle different capacities. So let's say this racks has different capacity. With this, we can just simply put different, cooling system in each racks, which is also often, found in the industry. And we also have to sorry, this is cooling. In rack cooling, so yeah, it basically just like a closed loop cooling to use some liquid, cooled liquid system to cool the system. Okay, let's us discuss about how we use computational fluid dynamics to design or maximize or make our system more efficient. From the previous discussion, we understand that slightly change in layout or maybe some containment system or maybe different strategy of rest floor will change how the system works in order to maintain the to prevent the circulation or maybe to prevent the mixing of hot and cold air that most of the time cannot be solved intuitively. So maybe if you are an experienced engineer, you can use your experience or your previous project strategy to apply. But most of the time, the HVAC system for data center is always unique. It means if you have different vendor or different requirements from different rack specification, or you have specific layout of the facility, it always have different strategy to be used and rely basically on the intuition will not works with the same with the unique design. That's why we help you to imagine how the flow will behaves with different scenarios using uh, numerical method. Basically, this is an advanced method used mostly in mechanical or civil engineers to design fluid and flow. Fluid and thermal physics. So it's not only used for HVAC. Basically, let's say you design a you know high hypersonic flight, let's say, vehicle, you will also use the same you know method using computational fluid dynamics. Okay, computational fluid dynamics in data center. So basically from the CFD computation, we can get some parameters. Of course, the first one is the temperature distribution. So we can see how the temperature distributes in the cold aisle here and also the hot aisle. We can see the difference here. The orange one is colder than the yellow one, which we can expect the temperature distribution. And we can also see the velocity distribution. We can see here the local velocity from the perforated floors. And again, from this detail, we can we can see some local recirculating flow here. That's why this is so important to imagine your flow in a real way. How to say that? Imagine the flow in a real way. So basically, the simulation result will tells you how the flow behaves, and you can change based on the simulation result to iteratively change your model. And here we can see the detail of the rack's temperature. So we can exactly know where the rack has better, have a cooling, have efficient cooling, physics, and which one has still hot temperature that needs more attention. And again, this is clearly show you how the recirculating flow might happen in the detailed manner. And this is the streamline again to see the flow or maybe some unnecessary recirculating or maybe some unnecessary eddies here, which dissipates a lot of energies that maybe we can streamline by make some containment or something like that. Okay, and we can also see the detailed, let's say, around the racks or maybe around the tiles. So you can choose the best specification of your tiles. Let's say, I don't know, you just like hypothetical situation, or you can even modify your racks, let's say, or maybe choose the best velocity to make sure that it passes through the racks without losing large amount of pressure drop, but still cools properly, something like that. Yeah, the idea is to see the detail so you can make your decision based on this detailed information. And yeah, the last thing that I want to discuss is we want to introduce you to the Tensor HVAC Pro, which is dedicated CFD simulation software, flow and thermal simulation for HVAC system. So it is basically designed for HVAC. So like I said, CFD is a very advanced tool used to design some advanced technology like maybe hypersonic aircraft, or maybe some complex chemical reaction or combustion, let's say. So sometimes if you are architect or maybe civil engineer or maybe mechanical engineer that just want to design a HVAC system, just want to design the ducting or maybe the handling unit, sometimes you will be stuck on the theoretical, knowledge. Let's say you have to decide which turbulent model is better, or maybe how to prevent the mesh error or something like that. But in this Tensor HVAC Pro, we eliminate those problems by make it uh, dedicated for HVAC, so you don't have to worry about those burden. Okay, let me do a simple demo to show you how to use this software. So basically, I already have the project HVAC for data center, and here, sorry. Okay, first of all, you can try this software for free. I will send you the link to install the software after this event, and also the record of this video. And yeah, this is basically the user interface of the software. So here you can see our model. We have walls and some simple racks, and we also have the inlets and also outlets here. I don't know, I just make this up. It's not supposed to be like this, but yeah, it's always right to, make some trial and error with your own model, and we will see how how it might behaves. This is the system. We have walls, we have some racks, and if you notice here, we have also detailed tiles and also racks. So if you are CFD users, you will immediately notice how hard to generate mesh around this kind of geometry. It will take a lot of efforts just how to manage how it works. But in this software, you don't have to worry about that. The software will do the heavy lifting for you. So you just simply define the global mesh resolution and also object mesh resolution. So the finer the mesh basically will make your simulation has better resolution or a higher resolution. But more of the finer the mesh, it will makes your simulation, longer to run. For the object resolution, it will makes your objects like the racks or maybe tiles have better resolution compared to the global mesh. You can update the mesh to generate the mesh. It will take around maybe 15 minutes for this complex project, or maybe if you are using free version with simple geometry, it will take maybe just 1 or 2 minutes. Okay, you don't have to worry much about this mesh. You don't have to, do some advanced stuff here. It just everything will be done under the hood. You can also check the mesh if you like, but we will skip this. Then we define our boundary conditions. Here we have 2 inlets. It will automatically detect we have 2 inlets here. And for the inlet, we can define the velocity in X, Y, and Z direction, both in the SI unit or maybe in British unit. And you can also use this calculator. You just click this link. if you want to, convert your CFM to maybe in a meter per second or feet per minutes. So yeah, most of the time the air handling unit will have CFM specification instead of velocity. And you can also define your temperature for the inlets. And the other thing, like the grills, we will set the temperature as driven. It means it will drive based on the, the velocity or I mean, the temperature around that object, the environment. And we can also define the constant temperature. Let's say you have specific racks with specific temperature. Let's say you can use the input temperature input. Okay. And for the racks, we define it as a whole rack. So we can define the temperature gradient. Again, you can click the calculator here to calculate how much the temperature gradient based on the heat flux and also the temperature. But if you have specific racks with different location, let's say I will show you in the one of the sample here, the rack 7, let's say, you don't have to select all of these surface as your rack. You can simply click one of the location, let's say here. You can then separate the face if you like. Click the save patch, and you can define individually based on that specific location. If you have some, specific spatial value around their value. But here we can just simplify this to the whole rack heat flux. 100 is just arbitrary number to make it faster. For the walls, let's make it driven, but actually you can also treat it in the same way as the racks. Maybe if you have some specific insulation system, let's say, or maybe have different. You want to, let's say, if you want to change the floor with different materials, which has different temperature condition, or maybe you have outside temperature that is different, like in the winter or maybe summer. You can also consider these inputs, but let's skip this for this demo. And here, I think we don't have to discuss this much. It's related to the thermal comfort that I don't think people will comfort in this room in a long period of time. So I don't know. We just maybe ignore this at the moment. Okay, then we can run the simulation in a couple of iterations. So, the longer the iteration will make your simulation, have higher accuracy. But the longer the run, it will take more time to your work. And here we can also make your running parallel. Let's say if your hardware has couple of cores, you can use it. You can use them to make your simulation faster. But faster the simulation will, the higher the cores will consumes more energy and dissipates more heat, like our discussed previously. And this is just residual plots. Just basically tells you if the curves going down, it indicates a good results. So it's basically like the number after zeros, like 0.0001, let's say. So yeah, as long it's not going up and pass through zero value, it will be fine. Okay, let's see our result here in ParaView. And yeah, we can check. Let's say we want to see the value in with the cross section. Or yeah, sorry. Let's make it feature H and make it a solid color and create some slice to see what's happening inside this um, system. Here we go. You can explore whatever you need, like the velocity, temperature, or maybe air age, and anything else like we discussed earlier. Okay, maybe that's all. It's a quite long discussion. Maybe in the other discussion, we will discuss more detail about the standards used to design this HVAC system from ASRAE, and that will be more interesting with specific values that we have to comply. But at the moment, we already have 1 hour discussion, so I will finish this presentation. If you have any question, please raise your hand. And again, after this session, we will send you the email for the recording this recording session, and also the maybe the presentation, so you can again review the materials. Okay, I think we don't have question in this session, so thank you for all for joining this webinar, and goodbye, good morning, good evening, and have a nice day. Thank you, everyone.